Mr. Rafi.
What subject are we taking?
What are we doing today?
I don't know.
You don't know?
What is this?
Enough. What are we doing today?
The first hour will be Dota, second hour will be studies,
I like Dota tutorial.
third hour we will watch Rafi doing video production.
I'm inside.
Yeah.
Okay lah. Free access to you guys.
Is this tutorial? No, this one's the last one. The next week no more.
I'm sure. Interesting, sir. This Adv Computer
So basically, bookmark this
Cinema, video on demand page.
Oh, part of the computer architecture we're learning.
Okay, so in this week's tutorial we have a sort of range of questions. The first question is on matrix multiplication. But this is actually multiplication on a 2D mesh. So we're given this diagram, and we're supposed to explain how the diagram works. So we have a matrix, we have a mesh of processors, and we feed a row of one matrix into one column. We feed a row we feed a column of the matrix into a column here, and similarly the next row into this column, the next row into this column, the next row into this column. And then we want to multiply the matrix A by the matrix B, so we take the columns of B and feed the first column of B into the first row of the mesh, the second column into the second row, and so on. So if you look carefully at this diagram, it's a little bit like a pipeline. You can think of each row of the mesh being a pipeline and each column of the mesh being a pipeline. So it's a sort of two-dimensional pipeline. And what happens is that in this first element, C00, it starts off by multiplying A00 and B00 and keeps the result, the product. And then in the next step, or the next cycle, it will multiply A01 by B10 and add that to the result. The next step, multiply A02 by B20 and add it into the result, and so on. So, if you look at an arbitrary processing element ij, the arbitrary processing element ij computes aik times bki for k from 0 up until n. Okay, but one thing to note is that after the first row and the first column, you have to insert a delay for the other rows and columns, because we want this element, for example, C10, to compute A10 times B00, but this element will not get B00 until the second step. So therefore we have to insert a one-step delay here, and similarly for this processing element, it wants to multiply A20 by B00, but it's not going to get B00 until after 2 steps. So we have to have a 2-step delay, and here a 3-step delay, and so on. Okay? So, any questions about how the algorithm works? So, the question then asks us, suppose the dimension of the mesh is m by m. How many steps will it take to complete the complete the multiplication of the 2 matrices? What's the total number of steps? Sorry?
3m minus 2.
3m minus 2. So where do we get that? Okay, so as I said, you can think of this as similar to a pipeline, but because there's a delay for the subsequent rows and columns, which will be the last element to complete the result? Which will be the last element? Okay, so this one down here, C and M, will be the last to complete the result because it has a delay on its rows and columns. So if we work out as for a pipeline, first of all we have a delay, and we have m minus 1 steps delay if it's an m by m matrix. Okay, in this case we have 3 steps delay because it's a 4 by 4 matrix. So there will be an m minus 1 steps delay, and then it's going to take m more steps to carry out the first multiplication in C and M, and there are n multiplications altogether, so after you've done the first multiplication, it will require the further m minus 1 steps. Okay, so first of all we take the delay, then we can calculate that it takes m steps to get to P processing element mm, and then m minus 1 steps are required to compute the complete product. So the total number of steps is 3m minus 2. questions on that? Okay, everybody happy? So let's go on to question number 2. So this question asks us to explain what is meant by arithmetic intensity, and also we're asked to describe what's called the roofline model for SIMD processes. So can somebody give me a definition of arithmetic intensity? What does it measure? Okay, so arithmetic intensity really relates the performance in terms of flops or gigaflops to the memory required to carry out those floating point operations. Okay, so in order to carry out a floating point operation, you have to access memory, and the memory you can the memory you can access in terms you can measure in terms of gigabytes or bytes, and the arithmetic intensity is a measure of the floating point operations per byte. So, for example, it could be gigaflop over gigabyte or flop over byte or whatever. So, in last week's question, we talked about having the correct number of memory banks in order to keep the floating point processor busy. So, this is related to the question of performance. And one constraint is the maximum memory bandwidth. Okay, so that determines how fast, how many bytes per second of memory you can get. So if you're within the maximum memory bandwidth, then you can keep your floating point processors busy. But once you reach the maximum memory bandwidth, then that is going to be a constraint. And what the roofline model describes is that there are two constraints really on the maximum performance you can get. The processors themselves will have a peak floating point performance, okay, which will depend upon the design of the processors. So one constraint is the floating point performance of the processors. The other constraint is its maximum memory bandwidth. And the arithmetic intensity relates the two. So the maximum memory bandwidth is measured in bytes per second or gigabytes per second. The arithmetic intensity is the ratio of the gigaflop to the gigabyte. So if you multiply the arithmetic intensity by the maximum memory bandwidth, you get gigaflops per second. Okay. So we're given two examples now, and we want to draw some diagrams and explain how this roofline model works. So we have one vector processor A, and we're told that it has a peak floating point performance of 100 gigaflops per second, and it has a maximum memory bandwidth of 160 gigabytes per second. And we're given another vector processor B. This one, we're told, has a floating point performance of 40 gigaflops per second, a peak floating point performance of 40 gigaflops per second, and a maximum memory bandwidth of 16 gigabytes per second. So we can draw the diagram for this. Okay, so the diagram on the left relates to the first vector processor, and the diagram on the right relates to the second vector processor. And on the y-axis, we have the performance in terms of gigaflops per second, and on the x-axis, we have the arithmetic intensity. Okay, so you can see that at a low arithmetic intensity, then it's going to be constrained by the memory bandwidth. At a higher arithmetic intensity, because you can execute more gigaflops per gigabyte, with a higher arithmetic intensity, it's not going to be the memory bandwidth which is the constraint, it's going to be the peak FP performance. Okay, and we can actually work out where this point will be. Can somebody tell me what this point will be for the first vector processor? How do you work it out? Well, you know that the memory bandwidth times the arithmetic intensity is going to give you the performance in gigaflops per second. So it's quite easy to work out where that point is. Okay, so for the first processor A, it's going to reach this point at an arithmetic intensity of 100 divided by 160, or 0.625. For the second vector processor, it's going to reach this point at an arithmetic intensity of 40 divided by 16, which is 2.5. So, to answer the question, what is the constraining performance? So what is the constraining performance when the arithmetic intensity is a half? Is it the bandwidth or the floating point performance? Okay, so for both processors, at half, it's going to be the memory bandwidth, which is the constraint. For arithmetic intensity 1, this one is now the floating point performance, but for this one, it's still the memory bandwidth. And similarly for 2, for the first processor, it's the floating point performance, but for the second processor, it's the maximum memory bandwidth. Okay, so any questions on question number 2? Okay, so question number 3 asks us to describe some various techniques in vector processing. Okay, most of this is bookwork, so you can, I won't go into too much detail because you can read it for yourself, either in the lecture notes or in the book. So the first question asks us, what do we do when the vector length is not the same as the length of the vector register? Okay, so in particular, we may have a vector that we want to process which is larger than the maximum vector length. Okay? So what can we do if our vector that we want to process, if the length is larger than the maximum vector length, the length of the vector register? So, what's it called? Well, we can use the vector length register, but how do we use it? Okay, we can use a technique which is called strip mining, and then we can use the vector length register to indicate how many elements that we have in our register. So if we have a very long vector, okay, so suppose our vector is of length n, and we have a maximum vector length of mvl. We can divide n by mvl to work out how many strips we should have. But it's quite possible that n is not exactly divisible by mvl. So in this case, we take the integer part of the division, and then we have some extra elements left over. So we can work out how many extra elements we have left over by taking the length of the vector and taking the mod operation with the maximum vector length. Okay, and then our first strip we can have at the beginning, and the first strip will be of length given by n mod mvl, and that will start at 0. And then after that smaller strip, we have a number of other strips. So we have n divided by mvl other strips, which will be of the maximum length that can be handled. Okay, and you can work out where each of these strips starts. So strip j will start at element n-1 plus j times mvl. Okay, so strip 1 will start at n-1 plus 1 times mvl, strip 2 at n-1 plus 2 times mvl, and so on. Okay, so by using that technique, even if you have a long vector, which won't fit into the vector register, you can still process it.
No, I was copying.
Okay, any questions?
Hello?
Okay,
Do you move more left? You
Yeah, yeah. What you want? Maybe like your mouth has to be close to the mouth.
Yeah.
No. Addition to is that to a mouse?
okay, so let's go on.
Skype, Skype.
What if we have some code that we want to vectorize, but this code contains an if statement. So we don't want to execute the operation on all of the elements of the vector. We only want to execute the operation on some of the elements of the vector. Okay, what do we do there? What's the technique there? Yes? What technique do we use when we have an if statement which indicates that only some of the elements of the vector should be operated on? Okay, so we have a vector mask register. Okay, so this vector mark register, each bit or each element of the vector mask register is just a bit, and this mask bit will indicate for that corresponding element whether the operation should be applied to that element or not. Okay, so if you have some code which contains an if statement, what you can do is to use the if statement or use the if condition to set the mask bit to 1 where the condition holds, and set the mask bit to 0 where the condition does not hold. Okay, and then if you execute the code in the then part under the mask, you can specify the mask vector. When you execute that code, what happens with the mask vector is that if the bit is a 1, the operation will be executed on that element. If the mask bit is a 0, the operation on that element will be a no operation. Okay, so we can set the vector mask register for each element in our vector. We can set the mask register to be 1 if we want to execute the operation, 0 if we don't want to execute the operation, and then that operation is executed under the mask. Okay, so I think you had some examples of that in the lectures. So I won't go into the details of an example, but have a look at this technique and make sure that you understand it. Okay, and then the the last question, what can you do if the matrix is sparse? So a sparse matrix is one that has a lot of zero elements in it. Okay, so in the sparse matrix, most of the elements may be zero, but some of the elements will be non-zero. But if you just represent a sparse matrix in the usual way, then you're going to waste a lot of space, because all the space where the elements are zero, effectively that space is being wasted. So there are some special ways of representing sparse matrices. There are a few different methods. I'm not going to go and describe them all, but you can look at the different methods in the book. One example of a sparse matrix representation is to use an index vector. So with this way of representing a matrix, instead of holding all of the elements of the matrix, you only hold the non-zero elements, and then you have an index vector, for example, which indicates the position of the first non-zero element in each row. Okay, there are different representations, but one common way of handling sparse matrices is to use this technique of index vectors. Okay, but again, please go and read about that.
Di sana ada tutorial yang calculation but it's part 2, but it's on part 2 is on cash and factor. Di sana betul lah. Cash is langsung.
Okay, let's go on to question number 4 then. Again, this question is about bookwork, so I'm not going to go into the details. I think you've covered most of the material in the lectures.
He won't come for lecture.
So, first of all, it asks you to explain what is meant by GPU and GPGPU. So, GPUs were originally designed for graphics processing. GPU stands for graphics processing unit, and originally the idea was that in your computer, as well as the CPU, you could have a GPU, and the GPU would handle a lot of the graphics processing, and that would offload that work from the CPU, and you would execute the graphics processing on the GPU instead. So GPUs were designed first of all for graphics processing, but they were designed for graphics processing. It's convenient to have a large number of quite simple processors. So these graphics processing units usually have a large number of processing elements, but those processing elements are quite simple processing elements. And then later, people realized that we could actually use GPUs for general purpose computing. And this is where the term GPGPU comes from. So GPGPU stands for General Purpose Graphics Processing Unit, or General Purpose Computing on Graphics Processing Units. And the idea here is that we can make use of the high parallelism in GPUs and use that high parallelism for general purpose computing. And we can go even further. We could actually have multiple graphics cards, so that you have parallelism within a single GPU, and you can also have multiple GPUs as well.
Because this GPU is just for other general purposes. You can use it for the other general purposes, like replace CPU. Is it? I don't know.
Okay, so
Just the general.
when GPUs were first used for general purpose computing, the way you program the GPU was not very easy because the GPUs weren't designed for general purpose computing, they were just designed for graphics processing. But when they started to be used for general purpose computing, some different programming models or programming frameworks were developed to help programmers write general purpose programs on GPUs. So one framework or one model is CUDA. This is a programming framework developed by NVIDIA. NVIDIA is one of the largest companies manufacturing general purpose GPUs. And again, I think you've covered this in the lecture, but the CUDA model is a multi-threaded model. You can have CUDA threads, and the CUDA thread is sort of the basic execution unit for a GPU processing element. But although this is multi-threaded, the programming model is still an SIMD model because you can think of it as being a multi-threaded SIMD processor where these threads are organized into thread blocks. But the way these thread blocks are executed is that we have a single stream of instructions. So each thread in the thread block is executing the same stream of instructions, but on different data. And then within the GPU itself, you can have multiple SIMD processors. So you have parallelism at different levels. You have threads within a thread block, which executes on the SIMD processor, and then you can have multiple SIMD processors. Okay, again, I think you've gone into the details in the lectures, so I won't discuss too much detail here. Are there any questions? Okay, so if there are no questions, we'll stop early today. There will be one more tutorial next week. Okay, there's going to be a tutorial sheet 11. So I'll cover that in the
What is the definition?
Self-study.
Okay, thank you.
Self-study, yeah. That's what you're supposed to.
Rafi, how do you feel after the tutorial?
Enlightened.
Kenna,
Yes.
what do you learn from this tutorial?
Nothing.
Nothing! Delicious? Huh? Nothing. Ishin? Ishin nothing.
Makan.
Makan.